Welcome everyone. For today's prep, we're going to look at the next example in DO7. So we're going to see an optimization problem involving, in this case, revenue. So let's read through it. Here we want to find the level of production that results in the max revenue, provided the demand equation for whatever product we're manufacturing and selling is P equal to 6 minus 1/2 X $1,000. All right, so let's just start with this demand equation. First of all, little p equal to 6 minus 1/2 x. What does x represent here? So x represents the number of items, the quantity. So it's the number of items that we're going to be producing and selling. What about little p? What does p represent? So when we're dealing with the demand equation, P, lowercase p, represents the price per item. That we can sell at a production level of X. So we looked at kind of the usual way these demand equations work. There's an inverse relationship between the price per item and how many items we want to sell. So generally speaking, if we want to sell more items, well then the price that we're going to be able to get for them is going to go down because we're kind of flooding the market. Or if we only want to sell a few items, well then there's going to be fewer available, so the price is going to go up. So little p here represents the price that we're going to sell each item, and x represents the quantity, how many items that we're actually going to produce and sell. All right, so that's our demand equation. This p equal to 6 minus 1/2 x. And let's keep in mind that there are units here. So what do we want to do? Well, let's read through it again. First thing we want to do is we want to find this production level. We want to find the level of production. So what does that mean? Really, that's telling us to find X. X represents the quantity. So to answer the question, ultimately, we want to figure out the X value. And the key word here is, or key phrase here, is we want to find the maximum revenue. All right, so the demand equation here is not the revenue function. So we actually have to figure out the revenue function first. And let's recall what that is. So revenue in general is equal to the quantity times the price. So X times P. All right. Well, we have this other equation that then tells us what lowercase p is equal to, what our price is going to be equal to. So we have our demand equation. That's telling us p is equal to 6 minus 1/2 x. So what do we have here? If we wanted to maximize the revenue, well, if there were no restrictions on X and P, well, just make a lot of items, charge a really high price for them, and then we'd maximize our revenue. Turns out we can't do that because we have this extra condition here, this demand equation that says, hold on a minute. If you increase X, well, then your price is going to go down. So you can't just pick the quantity and price to be anything. There's this extra relationship here. And we've seen this kind of setup before. This is one of our constrained optimization type problems. So this example is a constrained optimization. So let's go through the steps for these types of problems. So the first step is to figure out the objective which the thing we want to maximize, so revenue in this case, and we want to figure out the constraint, which we have here. So we want to figure out those two types of equations. So the objective in these constrained optimization problems is whatever we're trying to find the largest or the smallest of, the maximum or the minimum for. So in this case, we want to maximize revenue. So we've got our maximum or our revenue function here, our objective now. And the constraint is extra information that puts some limitation on our variables. So right now our two variables are x and p, and they can't just be anything. They have to satisfy this equation. So once we identify our two equations, the next step is to solve the constraint equation for one of the variables. And in this case, if we look at our constraint, well, it's already nicely solved for us. So we don't have to do anything further there. So that one's already done. All right, so then step 3. What's step 3? Well, we're going to take our constraint after we've solved it, and we're going to plug it in to our objective. So we're going to take our constraint here, and we're going to plug it in. And that's step 3. Actually, we'll maybe write it here. And what do we get after we do that? Well, we're going to get a one variable function. And so our revenue, after we do that, is going to be x times, well, let's replace the p with 6 minus 1/2 x. And this is perfectly good. So all we did is we took our demand equation here, plugged it in where we saw a p, and now we have this x times 6 minus 1/2 x. And usually a good idea to try and multiply it all out. So we end up with 6x minus 1/2 x squared. So distribute the x to the 6 there, and then distribute the x to the other one. All right, so now we're ready for the actual calculus of things. So now we're ready for really the optimization part. So we want to find and classify our critical numbers. Kind of the usual routine here. So let's do the finding. So how are we going to do the finding? Well, we use our first derivative. So let's calculate r prime. Differentiate. Now, right, this version here is a product. We don't know how to differentiate this version yet. So we're going to use the multiplied out version. And let's differentiate this. So the 6x differentiates to just 6. And then the minus 1/2 x squared, if we bring down the 2 and multiply it with the negative 1/2, that's just going to give us a negative in front. So we're going to end up with 6 minus x. All right, and once we have our derivative, there's two ways we can get a critical number. It's either where the derivative is 0 or where the derivative does not exist. And derivative not existing, we're looking for division by 0. We don't see any division by 0 here, so none in this case. And if we set our derivative equal to 0 and solve, we get x equal to 6. All right, so we've got our critical number here. Now we just need to make sure, is this actually giving us a maximum, what we want? So now we're ready for the classification part. So now we're ready to go on to our next portion here. We're going to do the classify. So when we do the classification, we have two different tests that we can use. First derivative test or second derivative test. Second derivative test is usually the one to go with. It's a little bit quicker. So let's state the name of the test we're going to use, second derivative test. And that means we need to calculate our second derivative. So go up to our first derivative here, differentiate. Derivative of 6 is just going to be 0, and then derivative of the negative x is just going to be negative 1. So our derivative here is just always negative 1. So then how we actually do the second derivative test is we take our critical number and we plug it into this second derivative. And when we plug 6 in, doesn't matter what you plug into this second derivative, you always get negative 1 out. So this is always going to be equal to negative 1. And the way to remember what the second derivative test says, negative second derivative means concave down, and then draw the concave down shape. And what this shows us is, yeah, we're getting a local max. And actually, this kind of gets a free upgrade. So because there was only one critical number here, anytime we only have one critical number, well, then if it's a local max, it gets upgraded to an absolute max. If it was a local min, then it would get upgraded to an absolute min. So because there was only one critical number here, it's actually a little bit better. Not only is it just a local max, it's an absolute max as well. All right, and that's what we wanted to find. We wanted to make sure we got a maximum for our revenue function here. So now the only thing left to do then is just answer the question. And the question was really asking us find the production level that maximizes the revenue. So our production level, where if we go to answer it, it's really the last step here. The question was asking, find the production level. And that was really just find x, code for find x. So we got x equal to 6. And we'll say items. All right. So the problem doesn't ask for it, but sometimes with these, we might be, it might tell us find the price as well. So if the problem asks for the price, we would take our result, the x value that we found, and we'd plug it into our price equation. Or the problem might say find the revenue, find what the max revenue could be. Well, in that case, we would take our x value and go to our one variable version of our revenue function and plug it in there. So let's just try out for price. So this is kind of a little extra here. Problem really wasn't asking for it, but what would be the price that we should charge to maximize revenue? So we already know how many items we should produce. We should make six of these items in order to maximize our revenue. Now, what price should we charge in order to maximize our revenue? So we're just going to evaluate. We're going to plug in into our P minus, or our P equals 6 minus 1/2 x formula. And we're going to plug in x equals 6. So when we do that, we get P is equal to 6 minus 1/2 times 6, which simplifies to just 3. And the only be careful here is, what are the units? Well, if we go back up, the units in this case, the price here is given in thousands of dollars. So the price we should charge is $3,000 per item. So that's what lowercase p is telling us. It's telling us how much to charge per item. Okay, but this problem really didn't ask for this part, but just to get a little bit of extra practice there. All right, so we'll try another one like this. Well, another type optimization in class. So we'll see you then. Bye-bye.